Hi everyone, today we're going to be doing a physics question and it's on Rutherford scattering, another physics theme E question. So an alpha particle is emitted from a radioactive source and is directed on a head-on collision course towards the nucleus of an atom with atomic number Z. If the kinetic energy of the alpha particle is E subscript K, a classical electrostatic calculation gives the distance of closest approach as this, and we're given three statements here. Okay, I think it's helpful, not only for you guys but for me as well, to just remember how to get this classical equation or calculation as it says. So essentially, an alpha particle is directed towards some gold or whatever foil that's relatively heavy. And there's obviously nuclei because it's made out of atoms. And so the distance of closest approach, yeah. So the only forces, it's assuming, the question is asking for the assumptions, and one of the assumptions is that the only forces acting on it is the electrostatic force, and the equation for it is E equals Q over R squared. But this is actually about the energy, so this is sort of irrelevant here. So EP equals Q over R, where, it really doesn't matter which Q is what, but they represent the charges. And I guess it is helpful. So an alpha particle is basically a helium ion, so it has two neutrons and two protons, no electrons. So in the AZX representation, this is what it would look like. Whoa, what's next after this? Oh, yes. So, let's just rearrange for R, which is the distance. We flip everything and okay. So the distance of closest approach, if you visualize it, when it's closest to the foil or whatever, because this is going to be positive as it approaches the nuclei full of protons. And the alpha particle is also 2+. And so because both are positive, they'll experience a repulsive force, which means and it's also sent with really high initial kinetic energy to the right. And so the force will be this way because theoretically it would be repulsive both ways. And so theoretically when it hits velocity equals 0, that's when it's going to be closest because it receives a constant force. Actually, no, it doesn't receive a constant force because the distance changes, but the idea is when velocity is 0, that's the closest approach. And when velocity is 0, that means all of the kinetic energy has been transferred to potential energy. And so we can also just write this as KQQ over EK. And so we're getting closer to this. Now we just sort of need to put in the charges, make it more specific to the situation. So let's say capital Q is the charge of the alpha particle. And since it has 2 protons, it's just going to be 2 times elementary charge. And so Z, Z is sort of the, what is it? X, Z. That's the representation. And so Z is the number of protons of the nucleus of the atom here. It might be gold, as in Rutherford's experiment, but it might be whatever else. And so we put Z because it's the number of protons, and each proton has an elementary charge. So it's also Z times elementary charge. And this is all divided by EK, the kinetic energy. And yeah, we just need to just combine. How do they have it? 2K, yeah. See, 2K. And then they have Z. And then, yeah, the E is squared because there's 2. And it's all over EK. So that's how you derive this equation right here. Okay, but that's not even a question. Okay, let's answer the question then. The nucleus is treated as a point charge. Yes, this is true, and we assume that the charge is uniform. So this is true. The nucleus is treated as an immobile white mass. Yeah, it does not move. We assume that because it's large enough, it does not move displacement or have acceleration, because relatively it's too heavy. It's like the same example as we feel a gravitational force to the Earth, but so every time we jump, we fall back to the Earth, but then when we jump, it's not really the Earth coming back to us because F equals ma and m is very large. So we just assume that the Earth doesn't feel any effect, and it's the same thing here. We assume that the foil here doesn't feel anything because it's too heavy. Like I think gold is like 170 something, the total mass, so it's like really large. So this is also true. A short range attractive nuclear force acts between the alpha particle and the nucleus. So this is the HL part because we learn about the deviations when kinetic energy is really high. So when it's really high, the alpha particle gets really, really close to the foil, and the reason why the protons in the nucleus are not expanding or exploding because all the protons repel each other is because of the strong nuclear force, or what they call it, the short range attractive nuclear force. But in this case, we just assume that the only forces that the alpha particle experiences is the electrostatic force and not the attractive force, strong nuclear force. So this is wrong in this classical equation calculation assumption, which means it's A. 1 and 2 are valid. Yeah, thank you.